Hi, today in Applied Calculus we're going to get to what we've been working toward throughout this whole curve sketching unit. We are going to do optimization problems. And so we're going to specifically look at some geometric optimization problems and some business applications. But optimization applies to any field you can think of. Optimization is the broad word for finding either a maximum or a minimum. And in any field you can think of, there's something you want to optimize. You might want to minimize cost, you might want to maximize your production, maximize profit, maximize how quickly you can deliver things, that sort of thing. So it really does have many, many applications. So I'm going to open with an example just to show you how one of these works, and then we'll talk about that strategy and look at some more problems. This one is very basic, but I will build up and have selected some that are more difficult to help you with your homework. So in this problem, I'm trying to build a fence for my new puppy Lady, and I have exactly 20 feet of fencing available in order to make this. And the question is, how should I orient that fencing to make the area as big as possible? So what do I mean by that? I could use that 20 feet to make a long and skinny rectangle, so almost like a dog run, that sort of thing. Or it could be more like this. It could end up being almost like a square. So I'm not making sure that my lengths add up to 20 every time, but that's the idea, is that with 20 feet, there are a lot of different ways I can make that rectangle and change, the sides, and that's what we're trying to determine. So here's my puppy. Here is a diagram. So if there's not a diagram and it is something geometric, then I recommend you drawing one. So we need to label sides. It's a rectangle, so I could have one side that's x, but then that forces the other side to be x because the rectangle has to have the opposite sides the same. But it does not say it has to be a square. And so just because those are x, this could be a different dimension y, and of course then the opposite side would also be y. So I have now labeled my diagram. Then I need to make a constraint equation. I don't mind so much that you know the fancy names, but I want to refer to them to help you understand. We're going to have a constraint equation and an optimization equation. The constraint equation is written based on some information you were given, something you are restricted or constrained by. We are restricted by the fact that we only have 20 feet of fencing available, and that is our constraint. So what does that 20 feet affect? It affects the perimeter. So we need to think about that. Perimeter is what you get as you add the lengths to the sides when you walk around the object, in this case the fence. So the perimeter is x plus y plus x plus y. Or in other words, you might have already known this, 2x plus 2y, right? We have two x sides and we have two y sides, and we need to add them all together. Okay, but they specifically told me I only have 20 feet of fencing available, and that I want to actually put that number in. So this will usually involve some number that they gave you in the statement of the problem. And that is my constraint equation. I'm going to come back to that because I'm going to need it to help me in my other equation, which we're about to look at. So now I need to write an equation for what we're actually trying to find the max or min of. So an optimization equation is whatever we're actually maximizing. So we would read the problem and find what we are maximizing or minimizing. So if we go back, I want to maximize the area. So my optimization equation should be an equation about area. And here's my dimensions that I've drawn. Area is just length times width, but I've labeled my length and width as x and y. So I have a equals x times y, but the problem is I'm ready to do my optimization techniques that we've been building up this whole unit. And what I would do to locate a maximum or a minimum, in this case hopefully a maximum, is take the derivative, set it equal to 0, find critical values, right, and so on. but I don't know how to take the derivative of something with two variables. Now, there's something called multivariable calculus, but I'm going to spare you. Okay, so we don't need that for what we're doing because we have another equation, that constraint equation, that can help us. So what we need to do, and that's what I want you to see, is the why of each step, so you don't feel like it's just magic that you're supposed to memorize. I have something I want to find a max or min of. We have done that over and over again. It wasn't a word problem, but it doesn't matter. We took the derivative, found critical values, because we know that's where those maxes and mins can occur. I look at this, I don't know how to take the derivative. I need a single variable. That's what motivates my next step. So I need to use my constraint equation and solve it for one variable. It doesn't matter which variable. I happen to solve it for y so that I'll be left with x's, but you could do it the other way. So I take my constraint equation, solve it for one of its variables. Solving for a variable means getting it by itself on one side. So I get the y by itself on one side. And then I'm going to substitute. So if y has to be 10 minus x, given my constraint of me only having 20 feet of fencing, then that has to be true in this area equation that I'm writing about the same situation. So I can replace y with this quantity that it is equal to 10 minus x, and that's exactly what a substitution is. So I replace y with 10 minus x, and then I could distribute. What I've done here is just stress that now it is a function of just x, which is what we're used to working with, just a single variable. It doesn't have to be x. So then I can distribute, and now I have my optimization equation in just a single variable. So once I have that, word problem doesn't matter. You are back to one of your previous sections. I have a function that I'm asking you to find the maximum of. Every time you're asked to find a maximum, you know you're locating those critical values. So you take the derivative, set it equal to 0, find critical values, and then we've got to verify that we really have found a max. So here's our function again. I need to find the critical values. I take the derivative, get 10 minus 2x. If there were any does not exist kind, I would think about that, but there aren't because there's no division or roots. And so I do equal to 0 to find critical values, and I end up getting that x equals 5. Now remember from our absolute max and min section that if we have just a single critical value, technically the interval for this problem you could say is open, because we could talk about the x's, but what it would end up being is like a less than 20, not a less than or equal to for one of our values. And so it'll end up being an open interval, so it'll be like that second derivative test work that we did. So I have just a single critical value, which means that I hope that's a max because they asked me to find a max, and I hope it's not a trick question, but I've actually done no calculus to prove that this is a max. All I have done is found that this is a critical value, which means it's a possible max or a min. Now, very early on, we used the first derivative table to verify that something was actually a max or a min. But now, when we have just a single critical value, we have talked about how we can use that second derivative test. So if it's the only one, we're going to use that second derivative test to verify. And so in my directions, I will give you hints like don't forget to verify. So this is 2 points on this problem right here, just taking the second derivative and plugging in. So make sure that you don't forget it. You'll see that I do it in all of my examples. So I take the second derivative. Now, in a lot of these examples, it ends up being a constant. It won't always, but it does here. Whatever your second derivative is, you then plug in this critical value, which is a possible max or min, to check its concavity to see which one it is. That's the second derivative test in a nutshell. So if it is a constant function, our second derivative, then no matter what we plug into it, you're going to get that constant. But remember, if it had a variable in it, we would actually plug our x in and compute that. But no matter what value I put, even the 5 that I'm testing, and I should show that I'm testing that, I still get the constant -2. What I care about is that it's negative, so I have this possible max or a min, a critical value. I check its concavity by seeing that the second derivative is less than 0. Then that means it's concave down. So concave down, I have a possible max or a min, it's concave down. What does it look like? It looks like a maximum. And so you should absolutely have this work. You're going to have to write an equation, make a substitution, and then do your regular derivative equal to 0 to find critical values. But we absolutely need to do this because a critical value, we have done nothing to prove it's actually a max. This proves it's actually a max by saying it was a possible max or min and its concavity looks like this. Oh, okay, it's a max. All right, so then we now know that that does result in a maximum, but we were asked to find the dimensions and then that actual maximum area. So the x equals 5 feet is when that'll happen, but the actual max would be an area. So remember that somewhere on our page where we solved to substitute, we already had y equals 10 minus x. So now that I know what x is, I'm just going to replace x in there and get that y is 5. Now in this particular example, it turned out that this was a square, and you might have already known that from other work you've done in other math or science classes. But remember, this was our warm-up question. Also remember that your work is being graded, not just your answer. So in general, you won't see, like we'll see problems where one side is a brick wall, so we actually only are using fencing on 3 sides, and so that'll change the outcome of it and that sort of thing. But this was our warm-up question. So the dimensions ended up being 5 feet by 5 feet, and then the maximum area was also asked here, and of course area is just the product of our dimensions. But be careful, and in general, remember to go back to the original equation. Now, our original equation happens to be the area equation, so we will do a equals xy, which is 5 times 5, and get 25 square feet. But for instance, if we had a volume formula and we had just found our dimensions, if you just blindly multiplied them, if you had a surface area formula and you found dimensions and you just blindly multiplied them together, you'd be talking about volume when the question was actually asking about surface area. So what we want to do is realize this is no different than our non-word problems that we used to build up to here. Whenever we had a critical value that resulted in a max or a min, we always plugged it back into the original equation in order to find the actual max value. And so that's what we've done here as well. So that's our warm-up question. Now we'll summarize what we've done. And so what we're going to do is, of course, read the problem carefully and analyze it, make sure you understand it. If you need a diagram, then draw a diagram and label it with appropriate variables. And then I'm going to need to write 2 equations, a constraint and an optimization equation. If that means I still have 2 variables in play, I will have to use the constraint to make a substitution into the optimization so that I have a single variable. Then I'm looking for critical values. So I take the derivative, set it equal to 0, find critical values, and then verify with the second derivative that I've actually found a max or a min as appropriate, and then go back and answer the question. So go back and look at what they were asking you to identify from that work. So here's an example where it's not just a regular old rectangle. Like I said, something else you might see is if there's already fence on one whole side or brick on one whole side, and then we are just doing fence on the others, then our perimeter of what we're constrained by, how much we have, would be just 2x plus 2y equals whatever number they told us. So this is a little bit different version where you're using part of a wall as part of your side. But do watch out for problems like this, as I have asked those on tests as well. So I wanted to help you with this because it tends to be one of the more difficult ones in the homework problems. So it says we already have 60 feet of stone wall. We're going to extend that, but then we don't have to use as much new fence and then make a rectangular field. Okay? But we're told that we only have 360 feet to deal with when we're doing this. So we are constrained by the fact that we only have 360 feet to use when we are doing the fencing part. So that's our constraint that we need to write. So I'm going to walk around the sides that we are actually talking about and add them up. So it's basically perimeter, except that we're going to exclude the wall that's already there because we're not using fence there. So as I walk around, I have x plus w, and then remember that the length of this side would be x plus 60, right? The x plus the 60 more, or 60 plus x, whichever one you want. So I have x plus w plus x plus 60 plus, if this side's w, so is that one. So we do have to think a little bit. It's nice that they gave us the picture, but then we do have to think about the rest of the labeling there as well. So I walk around, add up the sides that I'm actually using fencing on, and it has to be 360 or less, but if we want to maximize, then we want it to be 360. So then I've just combined like terms, and I have 2x plus 2w plus 60 equals 360. Then my other equation that I can write is, what are we trying to maximize or minimize? So I go reread the problem, and it says greatest possible area. That means I want to find the maximum of area. So the formula that I need to write and then eventually take the derivative set equal to 0, find critical values, needs to be an area formula. So area is just length times width. And it doesn't matter what materials make up the sides. The area of this rectangle is W times this whole length, x plus 60. So do be careful about that. W times 60 plus x, or x plus 60. Okay. So the issue is that I know I need to take the derivative of this to find critical values, but I can't because it has two variables. So that's where I use the constraint equation to solve for one of its variables. And so in this case, I happen to solve for W. And what does that mean? It means use your constraint equation to get W by itself on one side. That's all. And what we're going to do then is replace the W in this optimization equation, the one we're trying to take derivatives of, so that we only have one variable. So summarizing what we had before, we had our W times 60 plus x, but we knew that W was 150 minus x from our constraint equation, so we replace it and we do have to FOIL. So we'll have to do outers, the first to get 9,000, and then the outers plus the inners give us 90x, and then the last give us negative x squared. Now I have an equation of just one single variable, and I can do my regular process. So at this point, you are back in previous sections and should just be able to go straight through our normal process. So find critical values. I need to take the derivative, set it equal to 0. And what happens is I get just a single critical value again. And so instead of doing a whole like first derivative table or something, which your book might show you as an option, this is much quicker. So I got my derivative. It was 90 minus 2x. When I set that equal to 0, I add 2x to both sides, and I divide by 2 to get x equals 45. So I have this thing that's a possible max or a min, but I have done no calculus to prove that, what are we looking for, a max, that it will result in a max. So that's why I'm going to use my second derivative test. Very quick and easy, but I do need to do it. So I would take the second derivative. Here was my first derivative, so the second derivative would be 0 minus 2, or negative 2. And I take this thing that's a possible max or a min and check its concavity by plugging it into the second derivative. And what we see is that we get negative 2. I don't really care about the value. I care about the sign. It is negative. It is less than 0. And so when our second derivative is negative, our original function is concave down. So I had this thing that was a possible max or a min, and when I checked the concavity, it was concave down there, so it must be a max. And so you can have this exact same thing. You don't need to have more, but you really can't have less on your paper to verify that you have found one. So then our last step is to answer the question. So the question asked for those dimensions and then what the actual max area was. So for the dimensions, we already got 45. Remember that when you do a substitution somewhere else on your page, you already solved for the other variable. We had done it on a previous page as well. So I know that W is 150 minus whatever X is. So 150 minus 45 gives me 105. So I have to be a little careful because those aren't my dimensions per se, because we have the 60-foot wall, but the question asks, what is X, what is W? So X ends up being 45 feet, that extra bit on the end of the brick wall, and W ends up being 105 feet. So then what is the max area? Remember to go back to the original equation. Whether you do the 2-variable version or the 1-variable version doesn't matter, but you do need to go back to not a derivative, an original function. And so one version of that was W times 60 plus X. And now we know W and we know X. And so we can multiply and end up getting 11,025. And it is area, so it is square feet. So the units are going to count as a point as well. Now that we're in some real world problems, so do think about the units as well. So you can expect one geometric problem and one business-related problem. Now, the nice thing about the business-related problems is we don't end up having to do that substitution because we are already in a single variable. What you do have to remember, but you've had to know for previous tests, is you do have to know those business formulas. And so I've broken it down into steps to really kind of help you know what to do next. So this says a clothing manufacturer has, in order to sell X suits, so they sell suits, the price per suit in dollars is given by this little p. So remember, it's kind of annoying they reuse the letter p. Little p is that price demand function or that price per item function, and big P is profit. So let's be careful with how you write it. You might want to label it with the words little and big. So this is little p, and it's 180 minus 0.5x. And they've also know that the cost of producing X suits is given by the 2,500 plus 0.75x squared. So part A, just do the next thing. I have hints along the way. Part A just says find the revenue function. That was on test 1. So revenue, I have to know, is X times P, where if P is a function of X, then I need to account for that. So X times this function of P, and I'm going to have to distribute because that function of P had multiple terms. So revenue, that's all I'm asking you to do. There's no calculus here whatsoever. It's a business equation. So revenue is 180x minus 0.5x squared, and that's because we're going to need it in a second. So then part B says find the total profit. Well, the other equation that we need to know and should already know is that profit is revenue minus cost. Well, we now wrote revenue. That's why I gave you part A to help you with that, and we knew cost. So I need to remember to do revenue minus parentheses cost because cost has multiple terms. And then I can distribute to change my signs and combine like terms. All B was asking me was to write the profit function. No calculus here whatsoever. But it's because in the next part, the question actually gets to the calculus. How many suits must the company produce and sell in order to maximize profit? Now read these questions carefully because another question could say minimize cost or maximize revenue. So whatever function they ask you to maximize or minimize, that is the function you would take the derivative, set equal to 0, find critical values, right, verify with the second derivative, and answer the question. So that's pretty easy. Whatever function, that's the one we're using. Well, that's why I built you up, right, because they're asking you about profit. So it's the profit function they're asking me to find a maximum of, so that's the function I'm going to do my derivative. So I need to find critical values by taking the derivative. I get negative 2.5x when I do the power rule plus 180. I set that equal to 0. There are no places it doesn't exist. And solve, and I get 72. Now again, this says this is a possible max or a min, but I have not yet proven that it results in a max. So I need to verify with the second derivative. So when I take the second derivative, I won't always, but I do again get a constant, negative 2.5. So when I evaluate it at this possible max or min, this critical value, I still get negative 2.5. What I care about is that that's less than 0. If my second derivative is less than 0, then my original function is concave down. If I had something that was a possible max or a min and it looks like this, it must have been a max. And so now I've used calculus to actually show I have a max there. So what we've decided is the company must produce and sell 72 suits. You got to think about your units. So I get silly things like people telling me X is money. You can go back to the original problem, and it says that in order to sell X suits, so it tells me what X is, and that all these outputs were in dollars, okay? So that will come up. Okay, so the company must produce and sell 72 suits in order to maximize profit. So you should be able to summarize your findings. You should be able to use appropriate units because they're told to you in the problem. And then part D, so what is the maximum profit? Well, remember to find the actual max value. We plug this critical value that results in a maximum back into the original function. So it was profit we were dealing with, and we have to be careful because there were a lot of original functions, right? There was a little p, there was a little c, there was a little p, a big C, a big R, a big P. So what do I mean when I say the original function? The original function that you were actually maximizing, which here was profit. So here's my original profit function, and I'm going to evaluate it at my critical value that we already verified results in a maximum. And so I'm plugging in the critical value that we verified to be the location of a max, and I get 3,980. Now remember, the output of a profit function, a revenue, a cost function is money. And so that would be dollars, and we should be able to appropriately label that. And then the last question, and this is really where it all comes together and is a very real-world application, it says what price per suit must be charged in order to reach this maximum profit? Okay, well, the price per suit function was little p that was given back in the original problem. So the price per suit, sometimes it's called the price demand equation, okay, but that is little p. So our critical value that we verified gives us all these maxes is 72. This time we are plugging 72 into little p, the price per suit equation. When it asked what the max profit was, we plugged that value into big P, the profit function. So we're just plugging into the function that they told us to. All right, so I plug 72 into little p, 180 minus 0.5 times 72, and I end up getting 144. So what does this mean? It means the company should charge $144 per suit, because it's the price per suit function, in order to get their maximum. So that really is a real problem. So if you identify how many, because remember, if we overprice something, there'll be less demand. If we underprice something, we'll get lots of demand, but then we won't be making as much as we can. So if you identify how many you need to sell in order to reach a maximum profit, which is what we did back in Part C, then you have to price it right to make that happen. So that's great that you think that you'll maximize your profit for the week, month, whatever it is, if you sell 72 suits, but how can you ensure that you're going to sell 72 suits? It's all about the pricing and the demand. So this really is a very real application where then I say, okay, so that means if I price it at 144, I think I'm going to get the right amount of demand such that I will sell 72 suits so that I can maximize profit. So I hope you'll spend a little time with these. Most of you are business-related people if you're in this course, and this really is a very realistic example, and I hope you'll kind of associate with it. Now, because of that, usually these are not as bad. I didn't have to substitute, and you tend to kind of take to those business applications, but you do have to know your business formulas. But what I'm going to end with is another geometric formula, because I know those are a struggle. So that's another one that I always get asked about in homework. I wanted to make sure we did together. So this says we have a rectangular box with a square base, which is very important. And it is going to have a top, so it might seem silly that they said that, but there are problems where it doesn't have a top or a cover, so they're making sure you know it does. But it has to be 2,500 cubic feet. Cubic because it's volume, right? But the materials that it's made out of, right? So all the products we buy are in certain packages, and they have to think about that packaging to make it so that it's sturdy enough and it holds as much as it's supposed to, but it's as cheap as possible for them to make so that they can make more profits. So the cost per square foot of the bottom, because of the material it's made out of, is $2. So $2 for every square foot is how much that material costs. The top is made out of a different material, and it's $3 per square foot, and the sides are something cheaper, and they're $1 per square foot. So it says, what should the dimensions be in order to minimize cost? So whatever we are finding the max or min of, in this case minimum, that is the function that we need to write as an optimization equation. But if we did that first, which you could do, that's fine, you would realize, oh, I have two variables. This isn't a trick question. There must be more information. So remember, the number they gave us that restricts us about how big this box has to be, that is our constraint, and it'll help us make a substitution. So the first thing is envisioning the picture. We said you should draw a diagram. And so it does have a square base, which is good, because otherwise we'd have 3 variables, not 2 to begin with, length times width times height, right, for volume. But because it's a square base, then both of the dimensions on the bottom are x, and then just the height could be different, because it didn't say a cube. So this could be different, and that's why it has a different letter. So we are told that the volume has to be 2,500, and volume in general is length times width times height, but our length and our width of our base are the same. So it's actually going to be x times h, or x squared h, and we know that has to equal 2,500. So that's going to let us solve for one of our variables. It doesn't matter which, but sometimes one's easier. Solving for h would be easier because it wouldn't involve square rooting. So I will solve for h so that we can substitute, and then in our optimization equation only have one variable. So the optimization equation is the one that students get a little bit hung up on, but if you kind of slow down and just think common sense-wise as you walk around the figure, cost it's a mixture of surface area and money. So we are told a certain price per square foot, which is area of each side, which means we're talking about the areas of each side. So I need to walk around and look at the areas of each side and then incorporate the money part. So the cost is going to be the area of one kind of side times its cost per square feet plus the area of another kind of side times its cost per square feet, and so on. So first we're going to look at the bottom. The area of the bottom would be x squared, x by x, okay? That's down here. And we are told that the bottom is $2 per square foot. So what I'm doing is multiplying the area times the dollars per area. Now, of course, I could write that as 2x squared. And I will in a second. Then what's the area of the top? Well, if the area of the bottom is x squared, so is the top. But we're told the top is more expensive and costs $3 per square foot. Then the four sides, because this is a square base, are all the same. This has area xh, and that also has area xh. And we have 4 of those sides as you walk around. So I have 4 sides, all with the same area, and that area is xh, and their cost is $1. Okay, so you might want to pause it and kind of look at that. This seems to be the big hang-up for everybody, is writing this cost function. But we are simply finding the area of each kind of side and multiplying it by the dollar per square foot of that kind of side as described in the problem. And then, for instance, for the sides, we need to recognize there are 4 of them. So that's my cost, and I'll summarize it on the next page. Okay, so I had 2x squared plus 3x squared plus 4xh. I can combine like terms and get 5x squared plus 4xh. But as I said, this is the thing I'm trying to minimize, and so I want to take the derivative, set it equal to 0, find critical values, right? There's a chant for this too, but I can't because it has 2 variables. So that's where I go back and use the constraint equation. I've just re-summarized it here on this page for you. We had this constraint. If I solve it for one of its variable, I did h because that's easier and doesn't involve square roots. By dividing both sides by x squared, I can substitute because they have to be equal given the constraints of this problem. And now I will have just one variable. So I do have an x on the top and an x on the bottom, and they will cancel and leave just one x in the bottom. And I can multiply the number parts. And so I end up with 10,000 over x for that term. Now, if I'm about to take its derivative, I should rewrite it as x to the negative 1. I guess you could use the quotient rule, but it's a lot of wasted work. So now I'm ready to take the derivative and find critical values, and you'll see why we did our last problem in the absolute max and min, and I said it was just because I was worried about the algebra of it, and this is very similar algebra, so hopefully you remember that. So when I take my derivative, I get 10x minus 10,000 x to the negative 2. Now because I'm about to solve this, I want to say what does that really look like, so I am going to rewrite it as over x squared. Now you should take note that if we look for the does not exist kind of critical values, we would have one at x equals 0. But x equals 0 is not in the domain of this problem, because if one of the side lengths was 0, we wouldn't have a box, right? You would have no volume. So you're definitely not going to get a box that you can minimize the cost of. So I did think about it, but it doesn't end up being a viable critical value. It's also not in the domain of the original function. So that's another reason, but multiple reasons. So then I'm looking for the equal 0 kind, and as I said, this algebra is very much like a problem we did in the previous section. So first, I get one term on each side. Then I need to get the x squared out of the bottom. So I multiply both sides by x squared, giving me 10,000 equals 10x cubed. Well, now I need to get the x cubed by itself by dividing by 10. And so then I get 1,000 equals x cubed. And now I need to undo the cube with a cubed root. So I cube root both sides, and I get that x equals 10. So this is my only critical value. Therefore, I hope that it results in a minimum cost, but I have done no calculus that proves it is. I have only done calculus that proves it's a possible max or a min, because that's what a critical value is. So I have this critical value. Here's a summary of what my original function was in 2 variables and 1 variable. Yes. This one, it was still 2 variables. So here, when it's just of x, and my derivative, and so I need to use the power rule version of my first derivative to take my second derivative, and then I'll rewrite it so I know what it looks like. I'm plugging that critical value, that possible max or min, into that second derivative to check its concavity. I don't actually care what this is, but it's a positive plus a positive over a positive cubed. Everything's positive, it's going to be positive. So if I have a possible max or a min and my second derivative is positive, my original function is concave up there, so it must be a minimum I'm talking about. So don't forget to show me this work of taking the second derivative, which I did over here, plugging the critical value into it, and then summarizing what you found and that you understand it's based on the sign of that answer. So now I've really verified that 10 gives me a minimum cost, and I am ready to answer the question. Now, I think the question actually only asked me for dimensions. I just did an add-on. So the dimensions, remember, we found x was 10, and somewhere else on our page, we had already solved for h. h was 2,500 over x squared, so 2,500 over 10 squared, and we get 25. So my dimensions are that the bottom should be 10 by 10, and then the up and down was 25 feet there. And so if we were asked for the minimum cost, this is where I warned you in our first problem, if you just take these dimensions and blindly multiply them together, you're not going to be answering the question. That would give you volume if you even remember to do x twice, x times x. But the question, if asked, would be what is the minimum cost? So you go back to the original function, where by original function, I mean the function we took the derivative of to locate maxes and mins. So I go back to the original cost function, again the x or the x and h version doesn't matter, and I plug in what I have now found, and I see that the minimum cost is 1,500. So again, I don't think this particular problem asked us for that, but I wanted to talk about what happens, that we aren't just going to multiply our dimensions at the end. We're always going to go back to what we've been doing since the beginning of this unit, which was define an actual max or min value. We're plugging into the original function. So you've now seen multiple geometric ones and a business one, and as I said, you can expect one of each kind. I hope that seeing the whys of each step and seeing that even when the story changes and it's a different function, the process is the same, right? We have a constraint, we have an optimization, we make a substitution so that the optimization is in a single variable so that we can take the derivative, set it equal to 0, find critical values, verify with the second derivative that we've actually found the max or min we were looking for, and then go back and answer the question. So you did it. You got to the applied problems, and I hope you'll reach out to me for help if you're having any trouble with them, because I'll be glad to help. Then we're going to be moving on to the other half of calculus called antiderivatives, which you would think is the opposite of derivatives, right? We'll kind of be undoing what we've done before.